All right, welcome everyone. So today we have Simon giving us a talk on singular learning theory and a very theoretical part of it, the core algebraic geometry part of it. He will talk to us about real canonical threshold and its connection to jet schemes. During the talk, if you want to ask questions, Simon, do you want questions during the talk, or do you want it to be okay? So
Yes, please. Yeah.
yeah, feel free to ask your questions, or if you want, type it into the chat. Okay, Simon, take it away.
Okay, thanks a lot. Yeah, so the main goal of this talk will be actually to present mostly results that are in Watanabe or in the thesis of Xiaowei on the connection between singular learning theory and geometry and singularity theory. And at the end, I will explain this connection with jet scheme, which is a bit more new. But for this, I will start with some context and yeah, why maybe we should care about some aspects of this geometry, and also the sort of path from alignments to interpretability to aspects of geometry. Then I will spend some time talking about degeneracy of analytic functions and the real log-canonical threshold, so the sort of core geometry quantity that of SLT. Then I will sort of go into more detail into the asymptotic expansions of various quantity, in particular asymptotic expansion of exponential integrals, and what we can say about the IO of the term and maybe why they could be interesting. And finally, this connection between the real log-canonical threshold and jet ski. I mean, this first part is kind of has been covered in detail in some previous talks in the seminar, in particular the talk of Jesse and also in this the position paper that we wrote, so on this connection between alignments, structure, and generalization. But just to one slide pitch. So I mean, generalization. So in particular, generalization to new data is a really fundamental aspect of questions in alignment and in SLT more broadly. And generalization, by its very nature, depends really on the internal structure of the model. And in particular, and this is particularly acute for machine learning model and in particular neural network because they are degenerate or singular. So this means that there are many low loss solutions which can somehow compute or approximate the target function in very different way, a very different internal structure. And this internal structure is selected by the inductive biases of the training process. And so this is important to understand how that goes. And we expect, I think it's a reasonable expectation that to do this properly, you have to track the development of structure. You don't want to jump directly to the end of training because then you have no hope to sort of tease out the whole structure. You kind of want to go step by step. And this is summarized in this nice this nice picture. So the structure in the training data should lead to geometric structure in the loss landscape. And this is where we will spend basically the whole talk, this geometric structure in the loss landscape. Then this developmental structure in the learning process, so optimization trajectory. And then finally, the structure in the model. So why is SLT good for this? Well, SLT provides some tools to try to fulfill this sort of grand vision. So first, it's a theoretical framework which relates the geometry of the loss landscape, its particular degeneracy, and model complexity and generalization in the context of Bayesian statistics. And so that's the theory developed by Watanabe. Then it's been put into practice because there is a scalable estimator of this main geometric invariant. So this local learning coefficient, which is another name in this statistical context for the real log-canonical threshold, via MCMC and stochastic graded MCMC. There are lots of interesting connections with statistical physics and various aspects of probability theory, and also on the algorithmic side of program synthesis. And so this is really a solid foundation, but of course there is a lot to do to develop that into a full-blown theory. But still, there's been a lot of progress in the last year or so. I mean, the last because it's been established in many settings that changes in the LLC throughout training, they correlate with behavioral and internal changes in the model. And it does seem in some contexts where you can make this precise to measure aspects of model complexity and to measure generalization aspects of generalization. There's been lots of new variants of the LLC. So this refinement, which the susceptibility, singular inference function, which go somewhat deeper into the correlation between structure in the data and the model. Yeah, so there are many papers. So I wanted to include a long list of references at the end, but I didn't have time to do that. But so to go forward, we really need. I mean, the sort of one of the bottlenecks in this picture that I started with is somehow the insight into the flow of structure from data to model, in particular how this is implemented geometrically. And so in the context of SLT, which is Bayesian inference for a singular model, we can be precise because this is really mediated by the geometry of the Bayesian posterior distribution. So Dan and Will in their beautiful papers, Program as Singularity, propose in particular this idea of structural Bayesianism, which is this idea that the structure of the Bayesian posterior should reflect, should somehow mediate between the structure in the model and structure in the data and structure in the model. I mean, there are quite a lot of challenges, and I'm not going to talk much about them, but I mean, just to mention some of them. So one of them, which I will try to say a little bit in the next slide, is that in practice, training trajectory do not seem to come close to critical point, which is a bit of on the face of it, it seems like a big obstacle for this theory, which is based on singularity theory and critical points of functions. Another important point is that, of course, SGD, or more generally stochastic optimization of the empirical loss function in machine learning is not at all Bayesian inference. So we want to understand why we can use lessons from the Bayesian theory to inform things about SGD training. So this LLC estimation seems to work too well somehow. It's kind of there is a kind of mystery about this, which I just wanted to point out, which is that it seems that you get very robust estimates from very small number of samples, which is surprising and interesting. Another part which is sort of related to this restricted or refined LLC or susceptibility and so on is that so far, the one input for this refinement of the LLCs, you need to look at substructures in the data and the model, and so far it's kind of limited to the visible structure of the model, so like layers, attention, and so on. And it would be good to sort of use observables which come from, for instance, in mechanistic interpretability techniques. And then maybe finally this point that the Watanabe theory is really assumes IID data, and I mean there's active research on this topic to extend to, for instance, with the sort of the grand prize being SLT for RL. Okay, so sorry. So this slide is a bit full, but this is just a kind of cartoon picture to maybe explain why, at least a very cartoonish way of why this, for instance, this problem about trajectories not meeting critical points may not be such a problem after all. And one hope that you can have is that the structure of the data distribution will be reflected in some kind of decomposition of the loss function into more elementary and more degenerate losses. So you should think of these elementary things as maybe the loss on subtask or sub problems, for instance. And this is understood in for instance, in the simple case where you look at kind of modes decomposition, where you choose a good I mean, sort of adapted to your data distribution, orthonormal basis of the function space where the function that you're trying to approximate lives, and then this leads directly to writing your loss function as your population loss function as a sum over these over modes. The second part of the hope is that these loss functions are kind of updated. I mean, not necessarily one at a time, but because already in the case of modes, that's the hope is maybe more generally that SLT trajectories sort of do come, even though they don't come too close to critical points of the full loss function, they come close to critical point, and they're influenced by critical points of these L alphas of the modes. Then the hope is that the transition between critical point can be sort of tracked and corresponds to changes in computational structure, and that can be tracked by this idea of structural Bayesianism applied to the LLM. Okay, so I just want to say a little bit about the basic setup of SLT. So if you probably a lot of you, including the people who will watch this recording, are familiar with this notation, and we're not going to need the notation for very long because I'm going to go into geometry and sort of forget the statistics quite quickly. But just to fix on the idea, so we have a data generality distribution, we have a parametric model, we have a prior distribution because we're Bayesian, we have some IID data, and then we have these four functions which are in the end essentially basically two functions up to shift. We have the negative log likelihood, this function. We have its averaged over data, so which is just the cross entropy between the true distribution and model. We have sort of empirical relative entropy, and then the population relative entropy, the K divergence between the truth and the model. And again, so Kn is ln minus an entropy term, which doesn't depend on the W, on the parameters, and similarly for L. So essentially, from the point of view from the geometric point of view, there's just two functions, and then you can shift the level set. So yeah, I mean, what is the kind of main theorem of SLT which then implies the sort of various formulas that Watanabe understood, the sort of the formulas, the statistical learning theory formulas that Watanabe understood. This main theorem is a kind of asymptotic expansion of the Bayesian posterior distribution, or maybe more appropriately the unnormalized one. You don't divide by the normalization constant. And so this is this posterior distribution, and we see that it looks already like a kind of, I mean, it's a distribution, so it's an integral. I mean, it's something that you want to integrate with against some function, and so we already see a kind of exponential integral appearing. There's the exponential of this minus n log likelihood, negative log likelihood. Then this leads directly by just integrating the asymptotic expansion to the asymptotic for the Bayesian free energy, and so that's this famous free energy formula, which is from a practical point of view at this point really the key result in the series. So the fact that this Bayesian free energy, which I didn't recall the notation, but which is minus log of the normalization constant here, as a first sort of energy term or a loss term. Which depends on the loss at the optimal parameters, and then sort of secondary sort of entropic term, a log n term, which depends on this lambda, which is the local learning coefficient or real canonical threshold that we're going to spend some time studying. And then with some more work, you get things like more statistical learning theory consequences, so for generalization and training error, so like the generalization, base generalization. So this result combines two ingredients. I mean, basically, as we see here, this is an integral for a kind of exponential integral, but with a function which depends on n, right? So basically, you have to do two things. You have to control the difference between ln and its expectation, which over data, which as I mentioned before is just is L. And then you have to understand the integral where ln is replaced by ln. Then that's really a deterministic asymptotic, deterministic exponential integral, and that's something that then falls into the world of singularity theory. Just so before we get to those exponential integral, I'll just mention that a bit about the difference between L and ln or K and Kn. So Watanabe, I mean, the first step of Watanabe's approach is to control this difference between K and Kn and to write it in this way. So Kn is K plus or minus some kind of fluctuation term, which is of order square root of K over square root of n, and the rest. I mean, this psi of n is a random variable, which is in fact kind of secretly is kind of have to be distribution valued, and it converges to a Gaussian process with kind of explicit covariance. So now all the fluctuations in all the functional variance of the model is contained in here. So this does make a difference in the sense. I mean, there is quite a bit of work to compare expectations with respect to the posterior and with the sort of annealed posterior where you replace Kn by K. And this leads to what, for instance, this quantity called the singular fluctuation. But that's really not the focus of this talk. And just a very cartoonish picture of how I think about the difference between K and Kn. I mean, in 1D, which is a bit silly, but I mean, in the regular case, Kn is I mean, of course, it has some fluctuations, but the around the I mean the unique optimal parameter in the regular case, basically the effect of Kn locally is just to move the minimum to the MLE, to the maximal likelihood estimator. But still, we know, I mean, that around, I mean, as n goes to infinity, this Kn looks more and more looks more and more quadratic first of all, and and the MLE moves to the optimal point. In the singular case, this is quite different. I mean, there is this large this sort of flat region. I mean, that's what singular means in this context. And in that region, there is this term psi or psi has actually a sort of persistent effect which persists as n goes to infinity, and it's this kind of Gaussian process, or I mean, physicists would call it maybe this is a spin glass with many critical points, and there's kind of the accumulation of more and more critical points as n goes to infinity, even though the amplitude of the function goes to zero, but there's more and more critical points. So from this point of view, there's really a clear geometric difference between the. Okay, so now I'll talk about the real log-canonical threshold, and I'm going to define it directly in the context that is most interesting for us, which is the context of exponential integral. I'm going to take that as the definition because really that's what we care about, and then I'm going to give some other interpretations. As a geometric interpretation. So now we have a real analytic function, which I'm going to call f, but with this, you should think of f as k. We assume that there are some zeros. We don't necessarily assume that the f is non-negative, although I'm going to reduce. I mean, I'm going to assume that. So I'm going to make some comments in a moment. So we have this exponential integral. And the intuition is that, which comes from the Laplace method, or is the classical Laplace method, is that it's this integral concentrates asymptotically as n goes to around the zeros as n goes to infinity, and in fact around the critical points, which in this case are not necessarily the same as the zeros. And so we have this theorem by essentially Atiyah and Arnold Gusenja-Levarchenko. I'm not sure exactly who to attribute this with, which says that this is equivalent as n goes to infinity to some positive constant times n to the minus lambda times log n to the 1 minus mu, where it should be mu minus 1. Sorry, there's a typo in. So lambda is some positive rational number, which is this real log-canonical threshold, and mu is so I decided to use mu instead of m. I mean, Watanabe uses m, but I think, yeah, it's just, it makes more sense to use mu. So this is a positive integer, and so it's the multiplicity, or I think it also kind of makes sense to call it the real log-canonical multiplicity, because in singularity theory, multiplicity has a kind of a different. I see that Edmund is he's laughing at me. Okay, so this was kind of a global quantity. So this is a measure that, but in fact, this localized, this sort of comes from this is a very local phenomenon. This asymptotic integral. So basically, for every point in W0, you can define this local real log-canonical threshold, which measures the same asymptotic but locally, I mean, on a small neighborhood of the point. And with the property that actually the global real log-canonical threshold is the minimum of all the local ones. And what happens is that this quantity, this local real log-canonical threshold, is it's constant on some kind of stratification of W0. So yeah, so I wanted to include a picture, but I didn't have time to do that. But maybe I can just gesticulate with my hands. So you have somehow pieces of W0, like which are all submanifolds, and on which this thing is constant. And then what happens is that when you specialize to a point, when you go to the closure of one of these stratum, this can only drop. So we can also define the most degenerate locus, which is those. Sorry, this should be W star, W0. Those points where the log-canonical threshold and the multiplicity are attained, and this is the locus where the integral concentrates in something. Some examples. So that I took from a talk by Watanabe. So here you can the integral is here. So this is the integral of exponential to the minus x cubed minus y5 to the square. So this is the zero locus, and you see that of course this is for a fixed value of n, but you see that most of the integral is already concentrated around zero, and this is because at zero there's singularity which is as a smaller log-canonical threshold. And so what is going to happen as n goes into infinity is that the integral is going to concentrate more and more around this, and with a sort of rate that is controlled by the real log-canonical threshold. And here there's an even more striking example where here the zero set has two connected components. There's a point and a curve, but even though this point is smaller than the curve, I mean, it's zero-dimensional and one-dimensional. Actually, most of the integral, and asymptotically, all the integral concentrates around the point, because the singularity at the point is again more degenerate than along the curve. Okay, just the terminology to clarify this real log-canonical threshold versus local learning coefficients. I mean, this is just pure notation, just not to get confused. So the learning coefficient, the global learning coefficient of a model is defined as the global the global real log-canonical threshold of L minus L0. I mean, you take the minimum of L, and you sort of look at you arrange so that the zeros of the function are the optimal parameters. When the model is realizable, which means that for some W, this P the model is equal to the true distribution. This is just the log-canonical threshold of the function k. And similarly, you have a local version. So I mean, maybe it's not so intuitive why exponential integral should measure somehow degeneracy of function, but so it's maybe more clear when we measure this in terms of the sublevel set and volumes of sublevel set. So here the intuition is that a function degenerates if the locus where the function is small is big. And so we implement exactly that. So you look at the locus where the absolute value of the function is smaller than some epsilon. You integrate some test function over it. And then again, you have this condition, which I didn't mention as well, but if the test function is positive around W0, then you have a similar asymptotic, but this time as epsilon goes to 0. And that you can also present like this as kind of a doubling, constant, or yeah. So some examples. A simple example is the case of the sum of squares, because then, I mean, if you think of the volume interpretation, this is really just about the volume of spheres, and not even the sort of precise volume of sphere, but how the volume of sphere depends on the dimension, and the radius and the dimension. And the multiplicity in this case is 1. And the other sort of key case is the case of monomials, where the log-canonical threshold is then the minimum of the inverse of the exponents, and the multiplicity is the number of the number of variables where this with this sort of maximal exponent. And yeah, and there are a few more pictures. So nice picture of Jesse, where we see this kind of effect of volume, of degeneracies on volume. So for instance, let's just look directly at this most complicated case. This is very similar to the Watanabe example, where you have a line and a point, and again, most of the volume actually concentrates around this point. Because the log-canonical threshold is smaller, it's 1/8, yeah, and it's 1/2 from the line. So just to comment on the role of positivity, and before I sort of assume that everything is non-negative. So what happens is that, I mean, maybe the first thing to say is that in SLT, we only use the case where f is non-negative. So, and that's, I'm just going to do that for simplicity, but there are a few interesting things about this. I mean, to connect to the broader literature on singularity theory, and also in the future, maybe to understand the critical points which are not minima or local minima, it's interesting. So the first remark is that if f changes sign at a point, then actually the real log-canonical threshold is always less or equal to 1. So it behaves quite differently in this case from the non-negative case. And in particular, if the point is a smooth point or a non-critical point of the function, then it is equal to 1. That's easy to see. And when the function changes sign, then what you can do is actually can refine the log-canonical threshold into a sort of positive part and a negative part, and that's possibly what could be interesting like as a critical point. But now, let's just assume a non-negative. So first so I'm going to go through some. Yeah.
I have a question. That is the same. The ability to break them to pieces. That is the same maths as getting the log-canonical threshold for piecewise analytic function, right, at the boundary. So you basically and then you take minimum over the pieces.
Yeah.
So for example, if it changes sign, then you just like change f to modulus of f, and then it becomes a piecewise analytic function.
Yeah, you can do that, or you can think of just of the function. I mean, basically ReLU of f and ReLU of minus f. So the locus where it's And the theory also applies to these two cases.
But
the asymptotic theory.
Won't the boundary cause problem?
No, so you need a theory which takes into account the boundary, but that does work. That's also what Watanabe and and Xiaowei do.
Yeah. Cool. Thanks.
So one basic thing is that this real log-canonical threshold, because it's really about this sort of rough behavior of volumes and integral, it is invariant of the analytic reparameterization. So in particular, it's kind of scale invariant. So you can multiply your function by whatever you like. It's not going to change the real log-canonical threshold. So from that perspective, it's quite a coarse invariant. Another important observation is that if a function is less than another one, or again up to a constant, the log-canonical threshold has the same property. And so in particular, when two functions are so-called contact equivalent, which means that you have an inequality like this, then they have the same log-canonical threshold. And finally, or also very simple consequence of the definition is that the log-canonical threshold of a power is one, of a power r is 1 over r, the log-canonical threshold. So now the case of another, some basic classes of singularities, so Morse and Morse-bot singularities. So first of all, there is a general inequality, which is quite important, which is that for any again non-negative function, the real log-canonical threshold is less than d over 2. And there is actually equality if and only if the function is Morse, or also called non-degenerate at W0. So if the Hessian is positive definite. And so in statistics, that corresponds to the notion of regular model. So a model is regular if the W0 is W and K, the function K is non-degenerate at W star. And so for a regular model, the log-canonical threshold is half of the dimension. There is a more precise inequality, which is also useful, which is that actually the local RLCT is less than half of the codimension of W0. Sorry, it could be the local codimension of W0 as the point W star. Oh, sorry, there's a typo here. So here I wanted to say just assume that f is Morse-bot. So Morse-bot function has a useful generalization of Morse function. So which in this case, it really means that W0 is a submanifold and that the kernel of the Hessian at every point in W0, well, okay, you need it basically at one point in. Yeah, sorry, I switched to the global version for some reason. Yeah. The kernel of the Hessian is exactly the tangent space of that submanifold. Then the log-canonical threshold is again half of the codimension. So this inequality is attained, and the multiplicity is 1. And this kind of statistic, this corresponds to this notion of minimally singular model. It's just different terminology on the two sides. So some results, both positive and negative, about some basic operations. First, the positive results. So if you have two non-negative functions which have depend on the disjoint variables, and basically they live on two different real analytic manifolds, and then you take the product and you take the sum function on the product. Then the real log-canonical threshold is additive. For the product function, actually, even with non-disjoint sum variable, this is always less than the mean, and in the case where the variables are disjoint, this is equal to the mean. But there are some negative results, which are one place where the theory is quite different from the sort of complex singularity theory, the analogous results to complex singularity theory. So first of all, there's no inequality between the and if you don't have disjoint variable, there's no inequality between in either sense, either way, between the lambda of the sum and the sum of the lambdas. And similarly, there's no inequality between the lambda of a function and lambda of its restriction to a submanifold, which is also something that can actually is controlled in the complex case, but not in the real case. And the function f when you deform f, the log-canonical threshold is also not. So this statement is not really super precise, but basically, it's not, you can't really control in general when you deform the function. Whereas in the complex case, there is a semi-continuity phenomenon. So another sort of general principle which is useful to bound the real log-canonical threshold is using the Newton polyhedron and the Newton distance. So I'm not going to, and unless you've seen this before, this maybe we've seen a bit cryptic, but basically you fix a system of local coordinates, and you write f as in terms of monomials, and then from these monomials you can define a polyhedron in RD, or RD to the RD. Yeah, in this quadrant of RD. And then the Newton distance is the minimal number such that delta delta, like the vector delta, 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 delta. So that's what it is in this polyhedron. Then a result of Vashenko, which maybe in the real case, I'm not sure exactly. Okay, so it certainly is very well presented in the thesis of Sherwin, is that the lambda is always less than 1 over the distance. And you can actually present this in this way, which makes it clear that it's kind of a linear programming problem, at least when you're finitely many. Well, it's a linear programming problem. So, and there are cases where this inequality is actually inequality. So this is the case of so-called Newton non-degenerate function. So this is okay. It's a bit of a complicated condition, right? So it's basically saying, I mean, if you take a face of this polyhedron, or a compact face of this polyhedron, that you can sort of select a subset of the monomial of f, and you ask that this function, the sum of this subset of monomial does not vanish on the torus or on RD star. Okay, so yeah, maybe the most important case, I mean, or the kind of usable case is the case where when you have a positive linear combination of squares of monomial, which is in some ways quite restrictive, and in some other ways, I mean, it does appear in concrete examples of in Bayesian statistics. They are Newton non-degenerate, and in that case, you have an equality. So in that case, you can compute it by linear programming. Okay, another useful result, and maybe I'll just talk about the second line, which is really the important one, is that if you can write, if you have a function which is a sum of square, but you can write it in a different way, with the sum of different square, but with other generators of the same ideal, then you get the same real-canonical threshold, and that's also a very useful principle to do some computation, because in particular in some cases that you can reduce to the Newton non-degenerate case. Okay, so now I'm going to move towards this sort of asymptotic expansion. So and this will involve the notion of the notion of the data function of so maybe in some way maybe the simplest analytic definition of the real-canonical threshold is that it's the supremum of those real numbers for which the powers are the negative corresponding negative power of f is integrable or locally integrable. It's kind of the cleanest definition, and it's in singularity theory, it's usually the one that's sort of taken as the basic definition. But you can actually say something more precise, because you can sort of turn this integral into a zeta function. So if you have some test function phi and some real number, and some complex number, and you start with a complex number with positive real part, then this integral will converge. And the point is that this has and this should deserve also the name theorem, and this is a theorem of Atiyah, really. This zeta function has meromorphic continuation, and the poles are negative real numbers. And now this statement becomes the statement that the largest pole is minus the real-canonical threshold. And it gives an interpretation of this the multiplicity, this real-canonical multiplicity, which actually is the order of the and this is proven like sort of all the basic theorems in this this proven using resolution of singularities. So I think unless you've seen this kind of statement and this kind of notation, this will be a bit cryptic, but if you so I'm not going to spend too much time on it, but basically it's a way to resolution of singularity is a way to really simplify by doing some transformation on the manifold, some change of variable on the manifold. It's a way to kind of drastically simplify the function to make it into a monomial function. But of course, the price that you're paying is that you are using this function, and this simplification only occurs locally on the new space. And so, yeah, using this is can still be quite a bit of work. But then you really get, in particular, you get a combinatorial formula in terms of the combinatorics of the exponent of these monomials for the real log-canonical threshold, and also for the multiplicity. And sorry, obtained here refers to is not clear. It refers to the meromorphic expansion, the meromorphic continuation of the data function, and basically this resolution of singularity reduces the problem of meromorphic continuation of the data function to the case of monomial just by base change. And the case of data function of monomial is can be done just by So one interesting aspect of this is that this leads to, I mean, first of all, it's really instrumental to the proofs of Watanabe, but in particular because it leads actually to a more precise asymptotic expansion of the exponential integral. So yeah, these formulas are maybe a bit complicated, but so just the starting point is just to write because this theta function has a meromorphic continuation, you can kind of write it at, as a kind of Laurent series. So you have these poles, which are this minus lambda k, and they have some multiplicities m, and the maximal multiplicity is mu k. And then in front of this, you have the coefficient, right? And this coefficient are just denoted by c, k, m, phi. And then the point, which is really this main analytic mechanism of this proof of asymptotic expansion, is that you can do two integral transforms, so inverse Snelling transform followed by a Laplace transform, and this changes this Laurent series into an asymptotic expansion of the exponential integral. So more precisely, so you still get, I mean, you still have the same coefficient, and you get this now you have n to the minus lambda k, and you have this integral, and then there's kind of a further simplification. I mean, this is not still quite the form that you like, but you just expand this with the binomial theorem, and so you get an expansion of the same type, but sorry, this mk should be in uk, sorry. Where this coefficient dkm phi, they are related to the original ckm or ckp by this formula. I mean, this formula looks a bit complicated, but in some sense it's not. I mean, the really complicated part in these formulas is are these coefficients, this ckm phi and this dkm phi, and passing from one to the other is through this formula is not so bad compared to the difficulty of actually computing the coefficients themselves. And those coefficients are actually, I mean, this is better than kind of a pointwise extension. This is really an extension in the language of distribution. So you have this like Schwartz distribution or generalized function. So basically, for every k and m fixed, the map which sends the text function to the corresponding coefficients has a kind of nice continuity property. Or basically, what this means is that it depends. I mean, that's basically what this means here. It depends only on a fixed number of partial derivatives of phi. It's sort of controlled by a fixed number of partial derivatives of psi. And you can actually be, yeah, maybe I'll just stick to that. And all these distributions are actually supported on the zero locus, and in fact on the I guess except maybe one of them on the critical locus of F. So I'll just show an example, a partial example. So just the case of the function x squared y squared, right? So in this case, these lambda k are half integers, and the maximal multiplicity is 2. So what this means is that for every half integer, I have to give you two distributions. One with maximal order 2 and one with order 1. So for instance, the first one that occur is, sorry, there's some constants, which, sorry, I did this quickly this morning. And so up to a constant, for instance, this first distribution is just the distribution that takes a test function on R2 and picks up the value at 0. So it's just what I could call it's the Dirac delta function at the origin. Whereas the coefficient of order 1 is a bit more complicated. So you see that you have these. This is a kind of so-called principal value of 1 over x at as a distribution that you apply to the function phi of x 0. So in a sort of very kind of cryptic notation, you could say that this is delta x, where this is delta x sort of sets y to 0 divided by y plus delta y divided by x. And in general, the higher coefficients are sort of linear combination of partial derivatives of those of the same basic distributions.
Is that second delta y supposed to have a parentheses, or is
yeah, sorry, it is
okay.
symmetric. Yeah,
they're the same thing. Okay.
So in particular, in these first two coefficients, you don't have derivatives of delta, but the derivatives of the delta functions appear later. Okay, so this expansion starts, and this is the most important term. It starts with the term with lambda k and m is our lambda and u. So it starts with this n to the minus lambda log to the. But now what we have gained maybe is that we have given a name to this to the constant, and we see that it's a distribution. And in this case, this distribution is actually not so bad because it's a positive measure supported on W0, and in fact supported on W0 degenerate, this sort of most degenerate part. And this is really the expression that is used by Watanabe to analyze, I mean to do SLT to analyze the partition function and the free energy, and via this but this is where you have to put back the sort of stochastic ingredient. And so then the sort of the two main ingredients for the analysis of by Watanabe are this distribution D of W on the one hand, and the process this stochastic process psi n on the other. You have to combine the two to prove the main results of SLT. Okay, so now I'm going to discuss a little bit some questions about these components, right? So, I mean, so at the level of what is the multiplicity first? I mean, at the level of the resolution, this multiplicity, as we briefly said, it kind of measures the maximum number of branches which compute the log-canonical threshold and which with a sort of non-empty intersection. And one possible effect of mu is that, I mean, a large mu means that the integral is larger than it should be for just looking at the LLs, the log-canonical threshold. And so this leads to a kind of systematic underestimation effect. But it's not clear what this effect is. We don't have much of a clue of what the typical value of the multiplicity should be for deep neural networks, certainly, and what the sort of computational meaning of that quantity is for various models. That's kind of interesting. And already one case that I don't understand really is the case of deep linear network, because so in the case of deep linear network, so by the work of Ayuagi and my work with Richard Grimani, we have kind of I think a clear understanding of what the geometry of the log-canonical threshold, but Ayuagi also provides a formula for the multiplicity, and I don't really understand what it means, like computationally or combinatorially. So then there's the constant term, so this D of phi. So I mean, this D of phi, if you look at the free energy formula, this is basically the deterministic part, so the part which is not comes from this psi process of the constant term in the free energy formula, or local free energy formula, where you sort of localize using the function phi. So it is, I mean, in that sense, it should be quite interesting, and it would be very good to understand it better. So in the regular case, we have a formula, and this has to do with the determinant of the Fisher information matrix at W star, or the Hessian of the population loss function. And again, I think there are lots of basic questions about computing this distribution in various cases. So in particular, in the minimally singular case, there's a computation by Evgeny, which so he did the realizable minimally singular case, but I think already it would be interesting to do it in the non-realizable case. It would be I think the case of like some toric situation like sum of square monomial, which, as I said, do come up in various statistical model would already be interesting. And I think the case of DLN seems pretty challenging, but I think that would be a really a good thing to do. Okay, so what about these higher order terms? I mean, I think there are good reasons to be skeptical that they are so important, but let's still think a bit about that. So, I mean, so first of all, I think they are very poorly understood, at least by me, but in general, it's I mean, even in the literature on singularity theory, especially in the real case, it is well known that there are it's difficult to compute even the poles, let alone the distributions. I mean, by their very nature, they should somehow be of decreasing relevance as n goes to infinity, right? It's not completely clear if, like, I mean, so you have this asymptotic expansion in the sense that if you cut at a certain order, then the difference is as a small order as n goes to 0, but it's not clear that as a series it converges. So and it's well known that asymptotic expansions in various places in physics tend to actually be divergent, even though they somehow, for every fixed order, they actually converge.
There's also the effect that at some point in the lower order, the psi process starts to dominate. The stochastic effect starts to dominate, and then you need to like the lower order term is only sort of meaningful in the expected in the expectation. I think like basically that you run into like way more problem in like little O of 1 terms, right?
Yeah. No, so there is also the effect of psi. Okay, so see, why should we bother in the context of SLT? I mean, I think there are some potential reasons, at least, and they are all sort of connected to it in some ways to each other. So one of them is that this, as I mentioned, this dominant term is really concentrated on this most degenerate part of W0, so it cannot really tell us about what's here in other regions, I mean, including on other branches of W0, which locally, which are not. Then there is the sort of case of vanishing. If you only compute the expectation of observables, which vanish at some order along W0, and I mean that seems a bit strange because we don't know what the W0 is, right? So, but that still doesn't mean, because if you have a property of the true distribution that you expect will be satisfied by the true distribution, even though it doesn't characterize it exactly. So of course, then if you could that, you wouldn't do any machine learning. But then you can still want to use that as an observable and compute and estimate posterior expectations. But then the effect of the then basically the dominant term can in this case can vanish, and you can see higher term. And this is already, this should already be has some effect in Watanabe's proof, because Watanabe does need to compute in his proof the expectation of k to the s. I mean, he only uses the dominant term, but actually already in that computation, there should be some. Like for higher value of s, this is less precise than for smaller value of s because of the higher order term. And also, so similar thing is that perturbations. Like if you deform the model again in a way that you expect will only lead to perturb, for instance, to deformation of the W0 of parts of W0 which are not the most degenerate part, or again for the same kind of result as there. Then, and this is important, I think, to interpret maybe correctly this results on susceptibility, or this could be important at least.
Simon, we have like 5 to 10 more minutes.
Yeah. I'm basically done with the asymptotic expansion. So I mean, there are some. So the point is that there are some results in the literature, but I mean they're kind of scattered about trying to understand asymptotic expansion, for instance, for the restriction of a function to a submanifold, then there are some like homological interpretations, so connecting to sort of the complex geometry and mean of fiber and so on. But it's not clear what if anything can be extracted, like what statistically meaningful thing can be extracted from all this nonsense. Okay, so now another connection with geometry is the theory of jet scheme. So, yeah, what's the idea? So first of all, we talk about arcs. So I mean, an arc is just a parametric arc I would just talk about arcs in RD. So it's just a germ of a real analytic map. So from some small neighborhood of 0 into RD, and we identify 2 arcs if they are equal on a smaller neighborhood. So basically, it's just giving yourself a bunch of convergent power series. And the arc scheme is just the set of let's say a sub set of RD, but is the set of arcs which starts at point in W. And we can also use formal arcs and formal power series. That doesn't really change anything at this point. Then there's the notion of jets, which you can think of as just equivalent classes of arcs in the where you identify 2 arcs if they have the same Taylor expansion up to order n. So this is a generalization of the notion of tangent vector, right? You know that if you've done differential geometry, that one way to define tangent vector on a manifold is as equivalence classes of curves, like parametric curves, which have the same behavior of, the same Taylor expansion of toward one, basically. And so in particular, unlike this arc scheme, this J infinity of W, which is a kind of an infinite dimensional gadget, it's not a finite dimensional manifold. This jet scheme is a finite dimensional manifold. And it starts with, so J0 is just W. J0 of W is just W, and J1 of W is the tangent bundle. So W here is still a manifold. So now you can, the interesting part comes where you look at the J scheme of functions. So you again start with some real analytic function, and you look at those jets on which the function f. So now if you have a jet, you can just pick a representative arc, and then you can, this arc is a little parametric curve. You can evaluate the function f, and now you have a map from some small interval to R, and you can just look at the Taylor expansion at 0, and you can ask that it's the first m coefficient, because the first m plus 1 coefficient vanish. And so you can think of this as saying that an arc, a jet is on W is in this M's jet scheme if the curve is kind of tangent to W0 up to order M, and this sort of where the notion of tangency is kind of measured by the function f. So this GM of W is now a real analytic subset of this ambient manifold, this GM of W, and it's quite singular. It can have many irreducible components. It's not a manifold; it can have many irreducible components. And the way to think of the irreducible component of GM of F is that there are sort of qualitatively different ways to be tangent up to other. And it's so this idea has been and these objects have been studied quite a lot in complex algebraic geometry in particular, but also in the real case a little bit less. And it's an alternative way to extract information from singularities of function. And one advantage is that unlike resolution, it's an intrinsic thing. It doesn't depend. There's no choice. And so what the connection with what we've been talking about is this formula of Mustata, which generalized to the real case. So Mustata did it in the complex setting of complex algebraic geometry, which is saying that so you look at the codimension of this jet scheme of the function inside this ambient jet, it's manifolds of jets on W. You divide by n+1 because I mean you remember that the dimension of Jm of W was go back. I mean Jm of W is just this guy, so its dimension is n times d plus is d times n+1. So it makes sense to sort of it grows linearly, so it makes sense to sort of divide by n+1. And then you take then what happens is that this thing admits a minimum, and that minimum is the real log-canonical threshold. You can also express it in terms of dimension if you prefer, and there's also a local version with what's the same. And so the interpretation is that your function is more degenerate if there are more jets. They are not really. You can recover the multiplicity, but there's not really. There's not really connection as far as I know, but so far to the higher terms in the asymptotic extension. Okay, so maybe I'll just try to give an intuition for the proof. I mean, there's in some sense it's quite easy, but I haven't still found the kind of optimal proof, I think. But so the condition that a jet is the jet of a function looks a bit like the condition that the value of the function is of order n+1. So it looks a bit like this. And what happens is that you can take a set of jets, you can lift them to arcs, and you can evaluate at some small t, and that produces elements in small level sets, sub-level sets of F. But a problem which I've been struggling with is that, but which the sort of classical proof deals with nicely, is that actually choosing relating the sort of volume of the elements you get in this way to the codimension of this is actually not so clear. But it's very easy to do when the function is a monomial function. And so the way that you do it, and this is basically the classical proof, sort of, but formulated in terms of reformulated in terms of volume of asymptotic volume of sublevel set, which is it's not the classical way to present it, but is to study the maps induced on jets and arc by a resolution. And then on the resolution, you understand how to construct jets which produce nice sort of volumes in your sublevel sets. But then you just need to understand the geometry of this induced map on resolution, and this is a very classical topic and you use the tools that's available there. But it would be nice if there was a way to directly unfortunately I thought I knew how to do this. Still don't know. Okay, maybe I'll stop here.